Hello, in this video we're going to take our first step into particle physics. Particle physics is the study of fundamental particles. These are the particles which can't be divided up into anything smaller. So we're going well into the microscopic here. These are the smallest things that we know of. And that's very different from the world that we see around us where we're interacting with macroscopic objects. So particle physics is something which is done in the lab. It's you've got particle accelerators and colliders, places like CERN and things like that. That's where scientists are creating these fundamental particles in controlled circumstances so they can study them. And then, as with physics and science, indeed in general, we're then looking to describe these fundamental particles, what their properties are, how they interact with each other. So it's the same end objective that we've got in all the other fields of physics. We're just turning our attention to these fundamental particles. Now, since the 1970s or thereabouts, the standard model of particle physics has been the main description or the main framework for describing these fundamental particles. And we'll take a closer look at that later on. The standard model is far from perfect, but it's the best description that people have come up with so far. So it's certainly worth a look. But before we get on to looking at what all of these individual particles are and giving them all this vast array of names that they've all got and such like, I think it's best to start with what these properties and interactions are, because it's the different types of interactions between fundamental particles that determines how we divide them all up and how we describe them, how we classify them. So that's the real driving force. In the lab, someone will see, oh yeah, these particles have interacted in a certain way. We'll give that interaction a name, and then we'll say that the particles that interact in that way have a particular property that means that they will interact in that manner. So it's very much observe the behavior and then give names to the different particles and the properties of those particles if they engage in a particular behavior. So really we want to start from that behavior first and then look at the particles afterwards. Okay, there are a lot of properties of fundamental particles, but we're just getting started, so let's focus on the most important ones. And really there are 5 that are most important at the beginning of particle physics. So we've got 4 that are associated with the fundamental interactions, and then we've got 1 which is called spin. Right, so based on the observations that scientists have made in controlled circumstances in the laboratory, they found that there are 4 ways that fundamental particles can interact. And we call these interactions at the microscopic level, at the particle physics level, because we're talking about 2, say, individual particles, which will then interact in some way by exchanging some particle between the 2 of them. And that will affect the energy and the momentum of each one of these particles. So it's a way of transferring energy and momentum between particles. So you've got 2 fundamental particles exchanging another fundamental particle in order to swap energy and momentum around. Now, that's what we call them at the microscopic level. We call them interactions. When these are aggregated up to the macroscopic level, these are our fundamental forces. So fundamental forces, fundamental interactions, we're talking about the same thing. It's just the difference in scale as to whether we're looking at the macroscopic or whether we're looking at the microscopic. But as I say, the scientists have observed that there are 4 different ways that these fundamental particles can interact. So they've given each interaction a name, and then each particle that engages in that interaction is said to have a particular property. So our 4 interactions are the strong nuclear interaction. So we've got strong nuclear, we've got weak nuclear, we've got electromagnetic, and we've got gravitational. So we've got these four interactions. Now, one of those we've already looked at, gravitational. We looked at that at a macroscopic level when we were doing classical mechanics. And we know that anything that has got mass will be involved in the gravitational interaction, or the gravitational force, as we were looking at the macroscopic level. So we can consider this to be one type of charge. This is like a type of charge that we can say a particle has. If it has mass, then it engages in the gravitational interaction, or more to the point, if it engages in the gravitational interaction, then we say it has mass. It has a mass charge, if you want. Electromagnetic interaction, although we haven't looked in these videos yet at the electromagnetism, you're probably familiar with the fact that this is an electric charge. So we say that things that are involved in the electromagnetic interaction have electric charge. For the strong interaction, we say they have color charge. And for weak interaction, we say they have flavor charge. Now, there is a bit of an issue with particle physics in that there's a split going on here between the forces or the interactions. That we've got particle physics is very good at describing the top three interactions here: strong nuclear, weak nuclear, and electromagnetic, but not so great at incorporating the gravitational force. So in gravitational force, really we're describing that using general relativity, which we'll come on to much later on. The top three here are described by different theories inside particle physics. So we've got something known as quantum chromodynamics. So that's chromo for color there. So yeah, we're saying it's got color charge, and it's quantum chromodynamics, which is describing the strong nuclear interaction. The weak and electromagnetic forces are closely related, and they're described by electroweak theory. And these are, we won't be talking about either of these. These are way too complicated for what I'm trying to cover here. But just be aware that these are in existence. So there are sub-theories inside all of this particle physics which are describing these behaviors in more detail. But these top three forces here are far stronger than the gravitational force. Yeah, if you give the gravitational force, say that's got a relative strength of 1, then even though we're calling this the weak nuclear force, it's 10 to the 33 times stronger. The electromagnetic force is 1,000 times stronger than that, and then the strong nuclear force is then 100 times stronger than that even. So these are much stronger than the gravitational force. The weak and strong nuclear force act over a very short range though. So the weak nuclear force will act over about 10 to the minus 15 meters. So this is very much contained to, say, the nucleus of an atom when these fundamental particles are grouped together. The strong nuclear force has got an even shorter range. So yeah, these are very localized, whereas the electromagnetic force and the gravitational force, these act just infinitely over distance. So most of the forces that we're experiencing, well, really all of the forces we're experiencing on a day-to-day basis, these are the electromagnetic and gravitational forces. So at macroscopic level, aggregated up. But we'll come on to that much later on when we look at these more closely. But we've got these four interactions anyway, and we're going to say any fundamental particle that engages in each interaction has this particular property in a certain quantity. So, it'll have a certain amount of electric charge, a certain amount of mass, a certain amount of flavor, and such like. and we'll be looking at those more closely when we get onto the standard model. Now we have got then spin, which is our final property, which is really important in particle physics. Now, spin is a key part of quantum mechanics. So quantum mechanics is, of course, where we're looking at the real, well, essentially looking at these fundamental particles and how things behave at the real microscopic level, the really basic level. Looking at quantum mechanics, and although we'll touch on it in later videos, but spin in particular, again, is beyond the level of what we're looking at here. But there's a couple of things that are important to know about spin, which is why I'm mentioning it. So first of all, don't think of this as being an actual mechanical, like we're looking at classical mechanics, if you've got some particle which is spinning around in some way. This is not a mechanical spinning in the way that we think of it in classical mechanics. So if you're spinning a top or a yo-yo or something like that, that's not what we're meaning by spin. But the important part with spin is it determines how a particular fundamental particle can arrange itself. So these observations, again, of these particles saw that some fundamental particles take up space, as in space has certain little slots that you can put particles in. And sometimes a particle will be in a particular point in space with a certain energy and momentum. It'll have a certain description according to quantum mechanics. The quantum mechanics will say, right, this is the quantum state of this particle. This is the state that it's in. And some particles then block others from having the same quantum state. It's like, okay, no, you've got one particle that's like that, and that's it. It's keeping the other particles out. It's a one at a time thing. And then they saw that other particles, they don't have this blocking going on, that you can have loads of particles all with exactly the same quantum state. And spin is one of the properties associated with spin is determining which one of these types of particle we're looking at. So this top case here, where you've got a one at a time setup where particles are blocking other particles, this is linking to what you might have heard of in quantum mechanics, the Pauli exclusion principle. So particles that have half integer spin, so their spin goes up in half, so a half, 1.5, 2.5, these sort of things, where you've got halves at the end. They obey the Pauli exclusion principle, so they take up space, and this is all the stuff that we can touch. So if things have half integer spin, then these are the things that we can touch. The things that have integer spin, so 0, 1, 2, for example, they don't obey the Pauli exclusion principle, so they don't take up space. These are things like photons, for argument's sake. So light, we don't touch light, we can't feel light. We can feel the energy that is transferring, but we can't pick up a photon. It doesn't take up space in the way that stuff does in the world around us. So these behave in different ways. So these are the 5 most important descriptions, most important properties that we've got on these fundamental particles. Which interactions do they engage in out of these 4? And then do they take up space or not? And it's these properties that drive the structure of the standard model, which is what we're going to look at in the next video. So we're going to go through each one of these, break up particles in certain ways, and then you'll see how that lays out in the standard model. Each one of these, each combination of these fundamental properties sort of corresponds to a slot in the diagram of the standard model, which we'll come on to next.